Okay, so we have the next talk by Yufan Zheng. That's computational complexity of Schrödinger operators. The floor is yours.
So hi everyone, I'm Yufan from University of Maryland, and today I'm going to talk on our recent work on the computational complexity of Schrödinger operator. And this is a joint work with Jiaqi, Yizhou, and Xiaodi. So without further ado, let's get started. So this is the Schrödinger equation as we know it. It governs the dynamics of quantum systems. And for most real-world quantum systems, the Hamiltonian in this Schrödinger equation usually takes the form minus Laplacian plus V, where minus Laplacian is the kinetic term, and V is usually called the potential term. For those of you who are more familiar with working on Hamiltonians acting on finite dimensional Hilbert space, this is the Schrödinger operator discretized over n-dimensional grids. So I'll give you two examples to show the prevalence of Schrödinger operators in physics. The first example comes from computational chemistry. This Hamiltonian describes helium atom. The second comes from condensed matter physics, and it describes Bose-Einstein condensate. And as we can see, after reorganizing terms in these two Hamiltonians, they recover the form of this simple Schrödinger operator. Also, recently, people have found that Schrödinger operators also have application in computer science, or more specifically, optimization. For example, we have this quantum Hamiltonian descent algorithm, or QHD, which explicitly utilizes time-dependent Schrödinger dynamics to minimize a non-convex continuous function. And also, people have found surprising connection between Schrödinger operators and the classical algorithm, stochastic gradient descent, or SGD. To be more specific, when you fix the learning rate in SGD, the final converging distribution will be equivalent to the distribution sampled from a ground state of a Schrödinger operator. So given its importance in both physics and computer science, it's thus natural to ask what is its computing power, or equivalently, how much computing power do we need to have to study them? Of course, we need to define computational power first, rigidly. So in Hamiltonian complexity, there are two main approaches to this. The first one is we can define the hardness, or the computing power, to be the hardness of time-independent simulation of this Hamiltonian. Or we can define the hardness of a Hamiltonian to be the hardness of the task to estimate its ground energy. And needless to say, these two tasks are also important in physics. But before proceeding to our result, one may ask, so why isn't this like trivial? Because like Schrödinger operator is like, it's basically quantum, right? Of course, we need a universal quantum computer to simulate a quantum object. So the reason we cannot trivially answer the question is the existence of clever algorithms for specific quantum systems. Those systems are quantum, but we have clever algorithm, classical algorithm, that efficiently computes the dynamics or some fundamental physical properties of them. For example, for non-interacting fermions, or for circuits consisting of Clifford gates, that's due to the famous Gauss-Mann-Neal theorem, of course. And for ferromagnetic transverse field Ising model, But of course, like, as we expect, more quantum systems are indeed BQP complete, which means basically we don't believe we will have any efficient classical algorithms for them. This includes scattering in QFT, and both Harbor model and almost every geometrically two local Hamiltonians. Okay, before proceeding to our main result, we need to introduce some necessary technical assumptions. The first one is we want to confine our system to be discussed into a finite hypercube, n-dimensional hypercube. And the second constraint we want to impose on the potential function is that we want its maximum and its maximal derivative to be bounded within poly of n. We make this assumption to avoid the situation that the system governed by this Schrödinger operator to be too pathological. Also, we assume that the potential will only consists of k-body interactions, where k is a constant. This is inspired by physical Schrödinger operators, because in physical worlds, usually we only have constant body interactions. So our result is, first, we show that, as expected, Schrödinger operator is indeed BQP complete. And for ground energy estimation, we found that it's Stokes MA complete, which is a bit surprising because we know that for general local Hamiltonians, the ground energy problem for them is QMA complete. And we don't believe that Stokes MA equals QMA. So this implies the ground energy problem for Schrödinger operator is maybe indeed easier. So let me further elaborate a bit on Stokes MA here. So Stokes MA generally characterize the difficulty of computing or estimating the ground state energy of a stochastic local Hamiltonian. So when I say stochastic, I'm basically saying that the off-diagonal terms of this Hamiltonian in computational basis is negative or 0. But here comes an interesting point. We know that both Harbor model is QMA complete. And actually, it's built from an underlying Schrödinger operator with some degree of approximation and truncation. So what's happening here? If it's built from Schrödinger operator with some approximation or truncation, why does its computational complexities suddenly lift it to QMA? And we don't exactly know the answer, but we have some speculation that might be because of that might be due to some irregularities or singularities in the potential function that's needed to realize the both Harbor model. But I think this problem is definitely worth more investigation. So let's talk our approach. For showing hardness, our approach is to do it by Hamiltonian simulation or Hamiltonian embedding. To be more concrete, we reduce a transverse Ising model or team Hamiltonian to a Schrödinger operator. And this is a well-established approach to embed the whole spectrum of a Hamiltonian into a low energy subspace of another Hamiltonian. But in our case, things become a bit more difficult because in previous works, people are usually dealing with finite dimensional bounded Hamiltonians. But in our case, this Schrödinger operator this guy is clearly infinitely dimensional and is unbounded. So we need to slightly invent some new technical tools to solve this problem, but I'm afraid that I don't have enough time to discuss details on this. So if we successfully build such a reduction, then the hardness of Tim Hamiltonian can be naturally inherited to Schrödinger operators. So we can ask, so okay, then what's the hardness of Tim Hamiltonian? So first, okay, from BH17, we know the ground energy problem for Tim Hamiltonian is Stokes-MA complete. And for time-independent simulation, actually, we don't find a result in the previous literature. So we proved it by ourselves that it's BQP complete. OK, but the proof is not so difficult because we found that we actually have all technical tools we want. So the starting point is that result from CMP18 that XS plus ZZ type Hamiltonian is, this guy is BQP complete. And we adapt a technique from this work to show that 3 local stochastic Hamiltonian is BQP complete. And then we use a Nolan embedding to show that 2 local one is complete. Then finally, we use this reduction, and we finally arrived to the result that Tim Hamiltonian is BQP complete, even if we want to simulate it time independently. It's worth noting here that the same technique cannot be used to show that Tim Hamiltonian is QMA complete. Okay, I should note that this XX plus ZZ guy here, it is QMA complete. So if all this reduction was out, similarly, then we will arrive at the conclusion that this guy is QMA complete too. But actually, this reduction breaks if we want to talk about QMA completeness. That's because this embedding doesn't embed the whole spectrum of XX plus ZZ Hamiltonian into the low energy spectrum of 3 local stochastic Hamiltonian. Instead, it embeds this guy into the middle of this guy's spectrum. So the ground energy isn't ground energy anymore. The ground state isn't ground state anymore. So yeah, for QMA completeness, this doesn't work. So we doesn't have like a surprising conclusion that QMA equals Stokes-MA. So let's talk about our proof idea of the reduction from Tim Hamiltonian to Schrödinger operator. So I'll illustrate it by showing you how we do it in one-dimensional case. That is, we embed a qubit into a bosonic mode with 1 degree of freedom. So the key step here is we map a Pauli X in the qubit space to a Schrödinger operator where the potential function is a double wave function. It it doesn't need to be a double square wave. It can be an analytic, like a quartic function double wave. But for ease of illustration, let's stick with this guy here. Okay, so assume that we have this mapping. What next? The next is we naturally embed the ground state and the first excited state of this guy, X, Pauli X, namely the plus state and minus state, into the ground state and the first excited state of this guy, X tilde, which is the ground state and the first excited state of a Schrödinger operator with a double wave function as its potential. And we know that its ground state will be the symmetric orange guy here, this curve, orange curve. And the first excited state will be the green guy here, the green line. And if we add up this orange curve and the green curve, what will happen? We'll find that the left half of this curve almost cancel out, right? And the right half of these curves adds up. So that means by our reduction, the cat0 state and cat1 state will naturally maps to two wave packets. They are geometrically apart. So in the third figure here, the cat0 state is roughly staying on the right half of the space, and the cat1 state is roughly in the left half of the space. So they are geometrically apart. Once we have this property, we can finally map Z. We can finally map Z into the sine function. So there's an important property that we can verify. So if we apply this Z, if we apply this Z tilde to cat0 tilde, we'll find that actually you are approximately equal to cat0 tilde again. This is because this cat0 tilde guy is roughly on the right-hand side of the space. And we know that for a sine function, it's a constant, it's 1, as long as x is greater than 0. So that means if you multiply them, this part on the right-hand side of the space will keep unchanged. Of course, the cat0 tilde state have some unwanted leakage to the left of the origin. So this will contribute to the error. Then our aim is, of course, to reduce this error, this leakage, to negligibly small, so that our reduction won't have any problem. And then this can be actually done by increase the middle barrier of this double wave function. But this comes as a cost. So as long as you increase this middle barrier, the whole embedding or the whole reduction will be more and more efficient. By efficiency, I mean to simulate the same Tim Hamiltonian, you need more and more energy represented in the magnitude of your potential function. You need more and more energy to simulate it. So we need to find a balance such that this leakage is small enough, but the energy is not prohibitively large. And we also have another problem that if you directly generalize our previous reduction from 1D space to ND space, then you will not get minus Laplacian, but you will get an anisotropic version of Laplacian. But this can be done by fine-tuning the double wave function along each degree of freedom. Okay, so far we have established the hardness of the hardness of Schrödinger operator by reducing transverse Ising model to it, and we know that Tim Hamiltonian is BQP complete and is Stokes-May complete, so we know that Schrödinger operator is BQP hard and Stokes-May hard because by reduction from one side to the other side, you only inherit hardness, right? And we also need membership proofs. So first, we will show that the Schrödinger operator time independent simulation is actually in BQP. But this is not too difficult because we already have algorithms by previous results. We just use them. And for ground energy program, so if you recall my first slide, you may recall that the Schrödinger operator consists of minus Laplacian plus V, and the discretized version of minus Laplacian is actually already a stochastic matrix. So what are we doing here then? yes, it is stochastic, but it's not local. So we need to use another embedding or reduction to make it fully local. So for some takeaways or future directions, for general Schrödinger operators, we show that it's BQP complete. You need full quantum power to study its dynamics, and it's Stoch MA complete, which is slightly more difficult than NP complete tasks. And we have some open problems. The first one, the most interesting one, is what exactly happened when we move to this first quantization Schrödinger operator to Bose-Hubbard model. Why is it suddenly become more difficult? And the second problem is we didn't impose any fermionic anti-symmetric constraint or bosonic symmetric constraint on the underlying wave function or underlying Hilbert space. So what if we impose these constraints on the Hilbert space? And that's it. Thanks for your attention.
Thank you very much for the talk. Questions? I will start from your first open question then. Do you have any intuition there?
Yeah, I discussed it a bit here. So, yeah, our guess is that it comes from, so when you try to build Bose-Hubbard model from general Schrödinger operator, there's a term, it's like a direct delta term, which is highly oscillating. So we guess the problem is because of that term, but we are not so sure. Because intuitively, if you have a direct delta, you can slightly smooth it out like to such that its derivative and it's known to be like poly of n, right? It shouldn't, intuitively, it shouldn't change the property of the system so much. But if you do that smoothing, like it's already like this Schrödinger operator, again, falls into our scope. So we have no idea what's happening there. Yeah. I encourage you guys to think of this problem if you are interested in. Yeah. We are confused about this.
Thank you. Any follow-up questions?
You spoke about, I guess the same question. You spoke about how when you go to the Bose-Hubbard model, it's becoming QMA complete. Right now you're at Stoch MA. Do you have any intuition for maybe weakening this operator so that it becomes BQP complete, the ground state estimation?
Oh, so we weakened this a bit?
Yeah.
Okay, so if we remove this guy, if we remove this minus Laplacian, then we know like if this is a purely diagonal thing with two local interaction terms, we know that this is NP complete, right? So yeah, so then we are leaving the quantum world to the classical world, but we are still in NP. So currently, I don't have a clear idea like how can we move from Stoch MA or QMA to BQP. Yeah, if we are talking about ground energy estimation.
Thank you.
Last questions? Okay, that doesn't seem to be the case. Thank you very much for the talk.
Thank you.